Yes, 4.1 is approximating the tangent line and applications of rates of change. So there's a couple things here. One, we're going to use the tangent line to approximate a function's value at some weird input number, okay? Something that's a little more challenging to plug in and just evaluate. And then we're going to look at some graphs and we're going to interpret some of that stuff today. All right. So the first thing we're going to be doing, that's what this is we can use the equation of the tangent line of a curve at any given point to approximate other values near that point. That's the key thing. And near, of course, is subjective. What might be near for you might not be near for somebody else. And so one of the things we're going to experiment with is how near do we have to be to get a good approximation? And of course, the closer and closer you are to that point on the tangent line, the more accurate your approximation would be. Sometimes it's not as feasible to pick a value that is very close to the point. And sometimes it's more feasible to find a point that's very close to that point. It just kind of depends, okay? And from problem to problem, we're going to make some evaluations on that. This process has a weird name. I think it's actually kind of made up, would be my guess. It is called local linearization approximation. The word that I think obviously is made up is linearization. I don't. But this is the description of what we've just been talking about. The word the phrase that describes that process. If you want to have your book open to 4.1, I am going to use some of the examples from there, and there's some pictures that I think are helpful. It's on actually page 77. I actually put the page on it. We're going to look at this number one. And then we'll just talk about what we're trying to do and talk about the idea of this after you get that in your notes. Let's just talk about what we're trying to do here, all right? So we have this graph. I'm gonna zoom in on it in a second. We have this graph of a circle, and we have this tangent line, and we have a point that lies both on the tangent line and on the circle. And what we're going to do is we're going to look at what the value of the function is at when x is 2.1. Now, of course, you could go in and you could plug 2.1 in and try to solve for y and do it that way. But what we'll find is that the process is simpler when we use local linearization approximation. It's such a mouthful. All right, so let's talk about what's going on here, okay? And then I'll zoom back out. So right here, okay, this is where the x value is 2. So at 2.1, just a hair to the right, we're going to pick a point that's on the tangent line, and that point is not on the circle. That's the key idea here. The points that we're choosing are on the tangent line, and if it's close enough to the circle, then it should be a good approximation. If I picked a point over here and I said x was, let's say this is 3, I don't know what it is. Let's say this is 3, okay? This is not a great approximation. Just look how much space there is between here and here. So the closer you are to that point that lies on the tangent line that is also on the circle, the better the approximation is going to be. That's the whole point. And when I was talking earlier about, your definition of near compared to somebody else's and it being a little subjective, the goal is to be close, all right? And you'll see what happens when we're far away. All right, so what we need to do is we need to write an equation for this line. That's what the process is. We're going to write an equation for this line, and then we'll end up just substituting that x value 2.1 in and simplify, and we'll get y. Okay. In order to do that, first we need the slope. And in order to find the slope, of course, that means differentiate this. And we're going to differentiate with respect to x, which means we have implicit differentiation. So I already went ahead and did that. Of course, this gives me 2x. This is 2y times y prime. This is just 2 times y prime. Okay, so that's that implicit differentiation piece. And then, of course, the derivative of 4 is 0. And so what we're going to do is once we solve for y prime, then we know the slope. And once we have the slope, then it's just algebra. You know, it's literally algebra 1. You know, use point slope, write the equation, and we're good to go. So go ahead and solve for y prime here. Okay. So obviously I have my y prime terms together. I'm going to factor the y prime out. This is one of the things I love about teaching this class is I can skip algebra steps. So thank you for that. We're going to move the 2x to the other side. I'm going to factor the y prime out, which is going to leave me with 2y plus 2. So I end up with the negative 2x over 2y plus 2. That is my y prime. I get your point. Yes. No, I did not simplify. I did not reduce by 2. But I'm not actually going to use this expression, right? Because I need the slope. Yeah. Oh. So in order to get the slope, what do I have to do now? I have to plug the point in, right? I have to plug the point in, and then I will get my slope. So that's why I didn't reduce, because I knew I was going to get numbers anyway. So what's the... Oh, fine. I could... Either way, you'll get the same answer. You can reduce if you'd like. Those of you who didn't reduce on the test yesterday, I did not take points off. I circled it. I made a note. Or I didn't make a note. I indicated that you didn't reduce, but I did not take points off. Unless it said simplify. Some of those said simplify completely or something. All right, anyway. So I'm going to plug 2 in for x. I'm going to plug negative 2 in for y. Okay. Even color-coded. So negative 4 on top. Negative 2 on the bottom. So my slope is 2. Okay. So we've learned that the slope of the tangent line is 2. And now we're going to write an equation for the slope of the tangent line. And we're going to write a general equation because in some of these problems, you're going to be asked for multiple values of the function at different x coordinates. So once you have the equation once, you can just use it again. Okay. So I'm going to use point slope. And so my tangent line y plus 2 equals 2, which is the slope, times x minus 2. Okay. So finding that tangent line first is important because, again, if you look, we're only going to go over A, but in your book, B gives you a different value, and you would plug that in the same kind of way. All right, so what we're trying to find is what y equals when x is 2.1. So what do you suppose I'm going to do? What am I going to plug in? What am I going to plug in and where? 2.1 for x, correct. All right. And now, notice here I went ahead and shifted from equals to approximately equal to. Remember, the whole idea here is we are approximating. Okay. So is that a huge deal? Would it be counted off on AP? No. Should you do it? Yes. Okay. So go ahead and simplify this and see what value we get for y. Here we go. So 2.1 minus 2 is 0.1. So that ends up 0.1 times 2 is 0.2. I'm going to subtract 2 over. I'm probably... Oh, no, I didn't show the work. Okay, 0.1. So this is 0.2. Subtract the 2 over. And so I should get approximately 1.8. Negative 1.8, excuse me. And if we look at our graph, we should be like, okay, it definitely should be a negative, right? It's somewhere in here. Definitely should be negative, still below the x-axis, so that's good. Okay, you're going to do this process multiple different times throughout the course of your homework. And they're going to ask you some questions about it, like, do you think this is a good approximation based off of your definition of nearness? So the reason why this is not the actual value, this is the actual value on the tangent line. It's not on the circle. There's only one point that is tangent to the circle. There can't be multiple points on that line that are tangent to the circle. It's only one place. So in reality, and I can't even zoom in far enough here to give you that, because to the naked eye, 2.1 looks like it's still touching the circle. If I had the ability to actually zoom in, and you could do this on a calculator, you would see if you zoomed in far enough. Now, 2.1 you might not be able to zoom in that far. There might be a point where the calculator gives up, is what I like to call it. When it finally gives you an error message, it's like, look, it's hurting my brain. The calculator's CPU is not even happy with that. So that's why. It is the actual value on the tangent line, yes, but that's not on the circle. Yes. No, other question?
Oh no, I was just gonna say, so like just have to look into an equation and then studying in that's value.
Correct. And so again, since the tangent line is not on the circle, we're looking for values that are on the circle. All right? Because oftentimes that would be a challenging thing. It's easier to go through this process. Plus, it allows us to think about what the tangent line means and how the derivative of a function and the slope of the tangent line, that we can connect those concepts together. Okay. All right, moving on to the next thing. And this is also in your book, and I suggest you screenshot it from your book rather than trying to take a picture of this. But we've got this graph, and it's very appropriate for our neck of the woods. And we'll go through it and try to answer some of the questions that are posed. So let's get that in your notes, and we'll talk about what's happening in the problem, then I'll let you do the questions. So as I was saying, this is a great model for us here. Okay, this graph represents the rate of rainfall in inches per hour from midnight to 6 a.m. during a tropical rainstorm. It's almost like this was... Did it rain more? It did. It rained a lot at night for Adalia, didn't it?
Yeah.
It could have been... This could have been us. It rained during the day, but in the middle of the night. Go ahead and try to answer these questions. Now notice it says write a complete sentence. Okay, make sure we're working on free response type questions where you have to be specific and include enough information, that kind of deal. Okay, so see if you can interpret this graph and answer those questions, and then we'll go through it and then we'll call it a day. Just notice that we have a little theme here, right? It's one thing to find the slope. It's another thing to describe what is happening, what that slope represents, and that's really the basis of this particular section, is trying to understand what the slope really means. Something I want to talk about before we even get into the answers. One of the things I think is helpful before you try to enter into some of these kinds of questions is to make a determination about what type of graph what type of function has been graphed. Is it a regular function being graphed? Is it a derivative function being graphed? Is it a second derivative function being graphed? Because those are really our three big options, right? The function graph is going to be a graph of position. The first derivative graph is going to be a graph of velocity. And the second derivative graph is going to be a graph of what? Acceleration. So what do we have here?
Velocity.
This is velocity, okay? So this is not... the whole dependent variable is a rate, okay? So that's important. So when you go to answer these questions and interpret these questions, understand that that's what's happening here. All right, so who would like to volunteer for 3? What point A means? Eliza, excuse me. I don't know why I said that. Go for it. What do you say?
At 3 a.m., rain falls at a rate of 1 inch per hour.
Okay. How many agree with that? Anybody want to change anything with that? I want to change the one little. Okay. Now, the verbiage, fine. I want to change the 0.0, the 1 and the 1.0. Okay. Now, I know we look at this and we think that 1.0 is actually 1. Why would they bother putting the 0.0 if it was actually equal to 1? That's the question I always ask. Because, and you could get into the discussion of sig figs and that kind of thing, and I don't want to do that. But what I recommend, just to be on the safe side, they put that 0.0 there for a reason. Is it an approximation? Is it exactly 1 point or 1 inch? I would argue, if it's exactly 1 inch, why bother putting the 0.0? So just to be a little safe, on the safe side, what you said was not wrong. But you get the point I'm trying to make? Okay. I would be there. And I know you use different words. that meant the exact same thing. Perfect. How many had something like that? All right, good. All right, somebody new for 4. Slope of the graph between points A and B. Isabella, what do you got? 0. Okay, easy enough, right? But we probably should say 0 inches per hour squared. Okay, don't forget your units. Does that mean it stopped raining?
It's the same rate? No. It's just constant.
Right, it's staying 1.0 inches per hour.
That's the next question.
Okay, oh, that is the next question.
Wait, how did that
So, man. Okay, so the rate of rainfall remains constant.
That's like my exact.
Between 3 a.m. and 4 a.m., the rate of rainfall, or the rainfall rate remains constant, or stays the same, something like that, right? It stays at, it's still raining, just the rate isn't changing. And that's the key, that when we identified what type of graph we were looking at to begin with, that was what's important. All right, somebody new, can we have some male representation here, please? No offense, ladies. Number 6, points B and C. What is the slope? -1 inch per hour squared. Okay. Okay. So when we take the slope of this, we're really looking at the slope, the derivative of the velocity. So that's why this one is acceleration. That's why the slopes have units that look like acceleration units, right? Because the slope of the velocity, the derivative of the velocity, is the acceleration. So that's why the units have to change a little bit. Okay? And then complete sentence to explain the meaning. So what's happening from time B to C?
The rate is
It does eventually stop raining, yes. However, it doesn't.
It's decreased.
The rate is decreasing.
Right, the rate of rainfall is decreasing. Yes, the rate of rain is decreasing. Okay, and it decreases at the rate of. So notice here now, the decreases takes care of the negative. So now my rate is no longer. We don't have to worry about the sign anymore. Okay, and yes, eventually it does stop raining. Okay.